Hello students, in this video we are going to learn how to solve cubical problems, and that too without using Kirchhoff law or Wheatstone bridge technique. Only using the symmetry rules how we can solve most of the cubical problems. There's a cubical network A, B, C, D, E, F, G, H. Now all these things are resistors. Okay, in the question it may be given all resistors are of a resistance R ohm, or resistance 2 ohm, or resistance all are of a resistance 3 ohm, or something like that. Or there is a different type of problems. This is the same only, technically it's exactly the same, only instead of resistors there will be capacitors. Okay, all the capacitors are of a C farad or 2 farad or 1.5 microfarad or whatever may be given, but all will be the capacitors. That's one type of problem. And these resistors, capacitors, these are not two type of problems. In fact, the idea conceptually those are the same type of problem only. But if we think types, what type of problems may be there? One kind of problem may be there to find out the net resistance between A and B. See, if it is asked to find the net resistance between A and B, it is same as finding the net resistance between B and F, or C and G, or G and H, H and G, or DH, whatever. That means the net resistance between two nodes which constitute any one of the edges of the cube. Okay, this may be one type of problem. And that again the variations like having capacitors, having resistors. Similarly, what is the net resistance between A and C if this is asked? So the diagonally opposite points of any one of the faces, like that 6 faces are there of a cube, right? So it can be between E and G, it can be between H and F, it can be between D and B, and so on. All will be similar. So this is the diagonally opposite points of one of the faces. And again there will be variations like instead of resistors, capacitors may be connected. So these all are type of cubical problems may come. So basically we will solve 2 or 3 problems today. So let us take up this problem, which is calculate the effective resistance between A and B if each of the resistor along the edges of the cubical network is of a resistance small r. Okay, few options are given: 2r by 3, 3r by 4, 5r by 7, 7r by 12. We will see how to solve it using symmetry rules. Okay, mirror symmetry and folding symmetry, the basics I assume that you already know, and if you have not known, I have made one video for a symmetry rules and a voltage distribution trick. You can search for that video with the symmetry rules, key physics. You can search and you can watch them and come to this video so that we can directly apply those tricks. Now symmetry rule we are going to apply over here. See, the thing is, between A and B we are going to find out the net resistance of this network. If you divide AB, then you can think of a plane like this, which will divide the network into 2 parts so that one part becomes the mirror image of the other part. Between A and B, you can imagine one battery. This will be some, let us say this is plus, this side, this is minus side. Now here, since all the resistors are R, D and E, these 2 points will be at the same potential. Yes, if 2 points are same potential, we can squeeze D and E into one point. Okay, a little imagination will help here. See, again slowly I am saying, from A, R resistance, same drop will happen, here also same drop will happen. So the point D and E will be at the same potential. So D and E can be squeezed into one point. And if this is done so, the mirror image of a D and E are C and F. C and F also will be squeezed into one point. Let me show point A and a point B. Okay, now AB is here, then DE is squeezed into one point. Let us say this is both D and E. Both D and E. DE are squeezed, then this point is H. Now see, if D are squeezed, this resistance will become parallel to this resistance, yes or no? Similarly, this resistance will become parallel to this resistance, yes or no? So, between these two, there will be two resistances in parallel, and between these two, there are two resistances in parallel. So, this, or this, and this, or this. So, between DH, one is there. Between HE, another resistance is there. All are of R ohm resistance. Between AD and between AE, one resistance are there. But when this is done, this side also, see, this is B, here G, at the level of H we are taking G, and CF are squeezed into one point. Similarly, CF are one point. Now see, this and this, when CF are squeezed into one point, these two will be parallel. Similarly, this and this will be parallel. Between AB there is one resistance, and between GH there is one resistance. So 10 resistances, but 12 edges are there. So how many resistors? This is covered, this is covered, but still there are 10 resistors. Which two resistances are missed? See here, between CD, here is one resistance, and between EF there is another resistance. See, between CD there is one resistance, between EF there is one resistance. Between these 2 points only there are two resistances. So we can connect it this way. So this entire network is reduced to this now. Clear? Now see, all are of resistance R. If two R's are connected in a parallel to each other, we can clearly see that these two are in parallel and these two are in parallel, like that these two are in parallel, these two are in parallel, these two are in parallel. Right? A and B, we have to remember that between A and B we are going to find out the net resistance, right? So all are R's. If two R's are connected in parallel, then the net of them is R by 2, R by R plus R, right? So R multiplied by R plus R, that is R square by 2R, that is R by 2. You know these fundamentals. So instead of these two R, I can put only R by 2. So wherever two R's are connected in parallel, I will put R by 2, R by 2. So instead of two R's in parallel, I can show only one R by 2. Similarly, instead of these two, I can show only one R by 2. Right? Similarly, instead of these two resistances in parallel, I can show one R by 2. Similarly, these two I can replace by using one resistance R by 2. Similarly, again these two, instead of these two I can show only one resistor of resistance R by 2. Now these three are in series, you can see clearly. So instead of these three, I can show only the net of this. So the entire circuit is reduced to this much now. Okay. Now just forgetting about the points, this circuit is becoming so simpler and simpler that why to the names only are creating confusion. Fine. So 2R is in parallel with R by 2. So what is the net resistance of this system now? Isn't it 2R multiplied by R by 2 divided by 2R plus R by 2? Now if we take 2 LCM, 2 will get cancelled. This is equal to 2R square divided by 5R. 2 into 2, 4R plus R, 5R. So 2R by 5. So instead of all these things, I can replace by one resistance which is equivalent to 2R by 5. So this is 2R by 5, R by 2, R by 2. These three are in a series now. So we can simply add, yes or no? So 2R by 5 plus R is equal to how much? 2R by 5 plus R by 2 plus R by 2 is R, right? So 7R by 5. Now this all together it became 7R by 5, which is in parallel with finally the R. So this entire network became reduced to this much now. Then what is the net resistance between A and B? R1 R2 by R1 plus R2. 7R by 5 multiplied by R divided by 7R by 5 plus R. So 5 if we take LCM, 5 will get cancelled. So directly what we can write? 7R by 5. So directly what we can write? So 7R square divided by, take 5 LCM, 7R plus 5R, 12R. 12R. 1R got cancelled with the 1R. So 7R by 12 is the answer, which is answer D. Is it clear to everybody? Now let us take up the similar problem. Exactly similar, but instead of resistors, capacitors are connected now. And it is said, just I change in the same question only, calculate the effective capacitance between A and B if each of the capacitor along the edge of the cubical network is of capacitance C. Each is of a capacitance C. Then some net capacitance options are given: 2C by 3, 3C by 2, 7C by 5 and 12C by 7. Let us see. Now again, between A, B we are going to find out. The thing is, it is exactly same as the last problem if we consider conceptually. But only difference is the series and the parallel connection of a capacitor's formula. A little variation is there. Now between AB, you can imagine one plane between AB which will divide the Q so that one part of it becomes the mirror image of the other part. Then you see D and E are having same potential and they can be squeezed into one. Similarly, CF can be squeezed into one. And exactly like that, what we did, the same thing we will be repeating. AB, you take A and you took B. Now DER you are squeezing into one point and H is here. H, D and E became 1 point now. Similarly, this side CF became 1 point now, and this is G and CF are squeezed into 1 point. CF are squeezed into 1 point. Now you see between AB there is one capacitor. These two, this we have shown, and between GH also there is one capacitor. This also we have shown. So this we are showing here one capacitor, parallel capacitor. Similarly here capacitor. Fine. Now here this side CF are squeezed. So this became parallel to this capacitor, and similarly this will be becoming parallel to this capacitor, and both will be joined together. So here also we can show capacitor. See, carefully observe DE. When DE are pressed, these two became parallel to each other and these two became parallel to each other. Similarly, when CF are squeezed to one point, these two became parallel to each other, these two became parallel to each other. So what is the left? C and D. Between these 2 points, one capacitor is the left. Again, EF. Again, between the same 2 points, another capacitor also left. So if we consider these two, then there will be one capacitor here and one capacitor here. So now again see all are capacitance C, it is said in the question, right? Then if two C's are in parallel, now parallel, if capacitors are there, simply it will be added, so it becomes 2C, 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 right? So this can be reduced to a network. Instead of showing 2C, I can show, instead of showing TCC in parallel, I can show 2C in one go. So 2C. Similarly, instead of these two capacitors, I can show only one capacitor with the capacity 2C, right? This is C. Instead of these two, I can show only one capacitor of capacitance 2C. Similarly, here I can show 2C, and here also I can show 2C, and this is C. Clear? Now these three, now we have to remember that we are going to find out the net capacitance between A and B. So these three are in a series. right? Then what is the net of them? 1 by C net is equal to, for these three only we are calculating, 1 by 2C plus 1 by C plus 1 by 2C. So take LCM 2C. This is 1 plus 2 plus 1. So 4 by 2C or 2 by C. But this is 1 by C net. So between this much, what is the net? C by 2. So instead of all these three, we can replace one capacitor only of capacitance C by 2. Now this C by 2 is in a parallel with this 2C. If it is a parallel, in parallel connection, it can simply be added up, right? So C by 2 plus 2C is equal to how much? 2 and a half C. 2 and a half C means 5 by 2C. So this is 5 by 2C. I can show only one capacitor here. Okay, I am erasing the names to avoid confusion. Now 5 by 2C is in series with this 2C and this 2C. Now of these three, if we will take out the equivalent capacitance of these three, how we will find out? 1 by C equivalent is equal to 1 by 2C plus 1 by 2C plus 1 by 5C by 2. So 2 by 5C. Clear? So this much is equal to, take LCM 10C, then 5 plus 5 plus 5C into 2 is 2, so 4. So this is equal to how much, right? 14 by 10C. But that is 1 by C equivalent. Therefore, C equivalent is equal to 10C by 14 or 10C by 14, yes, or 5C by 7. Now instead of all these three, I can put 5C by 7, right? This is 5C by 7. So this entire network between AB is reduced to this network now. But this 5C by 7 is in a parallel with the C. And these two are in parallel means the net between AB just you add up. So 5C by 7 plus C is equal to how much? 1 plus 5 by 7 times C, which is equal to how much? 12C by 7, right? So D is the correct answer. Is it clear to everybody? Now take up this problem. So I made a little change only. This is again a resistance of the cube only, but it is asking to find out the net resistance between A and C. And some options are given and we have to choose. Now listen. Between A and C, you can see that the entire cube can be divided into two symmetric halves. And since the line which is since the plane which is passing through AC is dividing it, this is a kind of a folding symmetry or voltage symmetry. That's why what we can say is D and B are at the same potential. What is the potential of a D? The image of that is B is having same potential, yes or no? Similarly, H is having same potential as F. So we can think that B and D are 1 point only and F and H are 1 point only. So when we squeeze B and D into 1 point, at the same time H and F into 1 point, how the network becomes? Let us find out. Now between A and C we are doing this thing. So B and D, when we will squeeze, that will join somewhere along the line joining A and C. So let us draw this. Let this point be A and this point be C. Okay, between A and C, B and D became 1 point. B and D. A little imagination again will help. B and D became 1 point between A and C, right? So when you join B and D as 1 point, now see, this and this will become parallel. B and D came together, so these two will become parallel. Yes or no? Similarly, since B and D came together, this and this will also be parallel. Yes or no? So between B and D came together. So between B and D and A, this happened, right? These two became parallel, these two became parallel. Similarly, this side what will happen? See, between AC we are doing this. Between EG same thing will happen. Let us imagine E here and G somewhere here. So between EG, HF are, you are squeezing H and F. H and F. So again, when you squeeze H and F, these two will become parallel and this will become parallel. Exactly same thing will occur. So I am just showing this, this. Now, between A and E, there is one resistor. Let's take this also into account. Between A and E, there is one resistor I connected. Similarly, between C and G, one resistor is there. This also I considered. All are R's, okay? I am not writing them to make it complicated. So, between C and G, we considered. Now, it became 10 resistors, right? But to which two are left? Between DH, one is left. Between BF, one is left. So, DH and BF, between this point and this point, both the resistors are there. So, let me write HF here. HF I wrote here. Between these two, we have two resistors. Within the same points, two resistors are there, means those must be in parallel to each other. Now, again, since all are resistance R's, so R are in parallel. If R and R are in parallel, then it can be shown as one resistor of a resistance R by 2. R by R plus R, that is R square by 2R, so R by 2. Fine. So instead of this, I can show R by 2. Instead of this, I can show again R by 2. Right. Instead of this all, I can show 1 R by 2. R by 2. Instead of these two, I can show R by 2. And instead of these two R's in parallel, I can show 1 R by 2. And between this and this, we need to find out the net resistance. And this is of course R, this is R, right? Now see, between this AC, we are going to find out the net resistance. And here, if you imagine, this shows a current symmetry or mirror symmetry, right? Between this, if you see here, let me erase all the points again. Names, it's not right now, we can understand it. So here, this becomes a mirror symmetry. Now, what is this side? Becomes the mirror image of this side. Then, what current flows here must be the current flowing here, yes or no? And what current passes here must be the current passing here, yes or no? And what current passing here must be the current passing here, yes or no? Then, if the current passing here is straightly passing and so nothing is going or coming, so this is meaningless, right? Similarly, if the same current is passing, now no current is going this side, so this part is meaningless. So this is a totally, there is no connection and this entire thing can be neglected now. So we can clearly see that this resistance, all these resistances are in series. So R plus R by 2 plus R by 2. This is 3R. This became, so R plus R by 2 plus R by 2 plus R. This became 3R. So instead of showing all these, I can show only one resistance which is equal to 3R. Okay. And so 3R, and these two are in a series again. So R by 2 plus R by 2, this is only 1R. So what is the net resistance between these two now? Very simple. R1 R2 by R1 plus R2. So 3R multiplied by R by 3R plus R, which is 4R. Right? 1R got cancelled with 1, 3R by 4. So 3R by 4. B is the right answer. Is it clear to everybody? Now let us take up this problem, which is exactly similar, only I have changed, instead of a resistance I made a capacitance. Now between A and C, it is asking the net capacitance of this cubical network, where all the capacitances are of a capacity all the capacitors are of a capacitance C. And this is exactly same like the previous problem, only resistors are replaced with the capacitors. So this is one home assignment, and if you solve 4C by 3 happens to be the correct answer. Now you will be interested to do it yourself. Wish you all the best.